Hi everyone, welcome to machine learning using Python. This is module 6, uh, second part, and what we call as session level. Session 11, this will uh, cover the what you call normalization, and then something to do with the what you call classification related to what you call the uh, regression, and something to do with the what you call the other factors which are advanced machine learning they call it, and Jamit will be able to handle that, and I'll hand over to Jamit to continue. And this is a probably 1.5 hour session. Hopefully we'll be able to record it. We the first one fell through. We are re-recording now. Thank you. Go ahead, Jamit, take over.
Thanks. So hi everyone, this is machine learning using Python. So the advanced machine learning topic covers some of the uh, learning models that we have already used, and we are getting more insights into them, or using some more advanced concepts on them. So this is module 6.2 and session 11. So our goals for session 11 are using regularization. Why would we use regularization? When we'll use regularization, and the parts of or some of the regularization which are rich, lasso, and elastic net. Then we'll be discussing about the K nearest neighbors and testing the KNN accuracy, as well as finding the optimal parameters for them. So let's get started. This is the IPL data that we have already been using. So it has these categories from age, runs scored, runs conceded, then highest score, up to the IPL team. So we have used this data set before also. So we'll be using the data set now with the same thing for undertaking these features, and trying to predict the player's selling price. So when we use the info method, you can see that there are a lot of object data types in the data set. So and so these object data types have to be converted into dummy variables, like you can see in the index 3, 4, 5, and so yeah, object 3, 4, 5, they contain the object data types. If so these are the first few records of the data set for the first 10 columns. So using these features from player name all and to other columns included, we'll be trying to predict the selling price of the players, and we'll be saving those into the sold price. So we'll be creating the X features or the X variables in order to give the input to the model. As uh, stated before, the categorical variables have to be converted into dummy variables for a linear regression model. So those categories will be converted and be saved into IPL auction encoded DF. So our X features are IPL auction encoded DF, and the Y feature is the sold price of the data set. So now we'll be standardizing the values of X and Y to get them into one scale, get them under one scale. So we'll be standardizing the values of X and saving them in the X scaled and we'll be standardizing the values of y. Now we'll be splitting the dataset into test and train and test for x and y value, y splits. So when we build the model using this linear regression and train the model on the train splits, you can see the different kind of coefficient values that we get for the uh, columns or the features we have used from the dataset. You can and as the comment says that the positive there are positive and the negative impacts depending on the sign of the coefficient values on the sold price of the player. So we'll be trying to see which are the highest or the most effective coefficient values from the IPL auction encoded DF and get the coefficient values from the model that we have trained and sort them in the descending order so we get the highest values first. So when we print this when we make the plots for the values, you can see the size of the plot shows the effect it has on the selling price of the player. So you can see the average ODI runs, then Sixers, country England, and ODI wickets. And these are the most effective ones. Now, some of the features can show high effect due to multi-collinearity, which are the test runs, high scores, strike rate of batsmen, etc. So these features should have a positive effect on the selling price. But due to multi-collinearity, it's not. So we have already trained the model, and so now we'll be trying to calculate the root mean squared error for the model on the predict and test splits. So we'll be defining this function and calculating the RMSE value for the model that we have created. And when we use this function on our model, you can see that we get the train and test score of 0.67 and 0.74 for train and test. Now it has a difference between them. So the score are meant to be more similar in both the train and test split, but it's not, and it can be due to overfitting on the training data. And overfitting can occur due to the model learning the noise or the noise within the dataset or the random fluctuations in the training data rather than the underlying pattern, which leads to poor performance of the model on the unseen data. So we'll be using a regularization in order to deal with the overfitting. So that's why we use regularization. When we think that the model is overfitting, we check it with the help of regularization. So regularization basically works by adding the penalty to the cost function. Now regularizations have two types that we are going to discuss as a LASSO, which is a least absolute shrinkage and selection operator. And the other one is rich regularization. So LASSO basically works by adding a penalty term, which in the end makes all the coefficients which are least important to be zero. And because it helps those coefficients to be zero, and we can remove those coefficients, it can also be used for feature selection of the model. In the ridge regularization, uh, we add the square of the coefficients to the loss function, or the uh, error in the mean squared error, which discourages large weights in the model, leading to a more balanced weights across all the features and reducing the impact of the outliers. So just to summarize both of them, rich term distributes the coefficient values across all the features. Lasso seems to Lasso reduces some of the coefficients to zero, which is why it can be used for feature selection. And so let's apply the L1 and L1, which is lasso, and L2, which is ridge regularization on the model that we have trained. So the ridge regularization, it takes parameter values of alpha. Here alpha is a regularization strength, and the max iteration that ridge takes and and the other parameter it takes is max number of iterations for the gradient solver. So when we fit the data for using the ridge regression and testing the train and test score, you can see that it has improved comparatively from the previous model, which is and right now we are getting the difference of from 0.68 on train and test score of 0.72. So we have a reduced gap between the train and test. Now we have used alpha value as 1 over here for using the ridge regression. Now we'll be checking it with alpha value of if equals to 2. And when we use it and increasing the max number of iterations to 1000. So when we use these and get the RMSE value, you can see that it has improved further, and the score that we are getting is a train of 0.682 and test score of 0.706. So as we have got an improvement, we'll move further with alpha value equals to 2 for ridge. Now coming to lasso regression, it takes two parameters, which are alpha and the max number of iterations. Here, we'll start the lasso regression with alpha value equals to 0.01 and the max number of iterations of 500. When we get the output values of the lasso and use those value of lasso to calculate the root mean squared error, we get the train value of 0.688 and test value of 0.698, which are very good score, as both the train and test are having almost similar values. So from as the values are very similar, we can say that the model is not overfitting. And as you know, as the lasso uses the least significant features and makes them almost zero in the coefficient values. So let's see which were the coefficient values. And when we use the lasso coefficients equals to 0 and its value equating to 0, you can see that wickets, ODI as strike rate, batting average, bowling, and playing role were the least significant ones. Now last is the elastic net in the regression. Now elastic net is the combination uses both the lasso as well as the ridge term in the error of the mean squared error. So you can see that it uses the gamma or the lasso regression term as well as sigma, which is the regression term. Now the default value is set to 0 for the alpha value of elastic net, and here alpha value is summation of sigma plus gamma, and the L1 ratio, which is between 0 to 1, and you can see the formula for L1 ratio equals to gamma plus sigma plus gamma. So moving further with the values of alpha equals to 1.01, and the individual values of gamma equals to 0.01 and sigma equals to 1.0. So the L1 ratio that we get is 0.001. So the elastic net parameters, alpha value, alpha L1 ratio, and the maximum iteration are given. For max iterations, we are going for 500, and fitting the model with the eNet within eNet and getting the values of the RMSE on the train and test bed, we are getting 0.789 and 0.665. Now the scores have worsened compared to the previous models, and the lasso regression was giving us the lasso regularization was giving us the best values. So we'll select lasso as our model. And you can see these are the scores that we got, and you can see that lasso is giving us the best score on train and test bed. So that's why we will be going further with lasso. So as you remember, we are using this IPL dataset, and these are the values out of which we are keeping these for the X features and sold price for the Y feature. Creating X features and then converting them into dummy variables, saving them into IPL auction encoded DF, and creating the X and Y features, X features from them. Standardizing the values to keep them under one scale, and then split the dataset, use the linear regression model, and see the coefficient values for the effects on what kind of effects it does. If we check the values in the descending order for the most significant or the most effective variables on the selling price, these are the variables that we get, the top ones. When we calculate the root mean square error on the test and the train set in order to see the performance of the model, we define this get train test RMSE and use our linear regression model. So these are the scores that we got on linear regression, and because of the difference, we check for overfitting. So we used regularization. We used for alpha value of 1 in that, and then checked the train test and train values, then alpha value equals to 2, and checked those values, which kind of reduced. Then for lasso, we did it for alpha value equals to 0.01, and we got a very good score. So that's why we selected the alpha value, lasso regression. We also checked the elastic net, but elastic net was not giving us a good value. In fact, it worsened the values. So now we'll be moving further to another topic on K nearest neighbors. In this session, we'll be covering only K nearest neighbors. And in order to discuss that, we'll be using a bank marketing data set where a campaign on phone calls of a term deposit plan is done. And we have to predict if the customer subscribes to the plan after the phone call. So we have to predict y equals to 1. So the bank data set that we are using, these are the values that these are the columns it has, and these are the some of the few records of the data set. You can see the age, job of the customer, marital status, education, default, and all the way to the last column being subscribed. So when we use the info method on the bank DF that we have used for reading the data set, you can see that we are having many object data types. Those object data types has to be converted. Oh, sorry. So first we will be checking on the values of how many values are there for yes and no on the subscribed column. So we have total 4,000 no's in the subscribed column and 521 in yes. So our data set is can be called as imbalanced data set because the number of one class is very large compared to the other one. So in such cases, the model, even if it predicts something that no customer will subscribe to the phone call, 88% of the time it will be accurate because of that imbalanced data set. And this is something what we call as accuracy paradox, whereas it is not actually accurate. So there are ways to deal with imbalanced data set. You can upsample the data set. Upsampling basically means increasing the amount of minority class, and you can downsample. A downsample basically means to reduce the number of records on the majority class. So the scikit-learn dot or sklearn.utils provide us a method called resample, which takes original dataset, replay, then the second parameter it takes is replace, which implements resampling, and with replacement, if false, all resampled examples will be unique, and the number of samples we want to create. So first we get the number, we save the number of no's in bank subscribed no and bank subscribed yes, and then we upsample the dataset and save it in DF minority upsampled. Now we create a new dataset called new bank DF for the upsampled dataset of yes present in the dataset with the number of no's that was already present. So now the total number of no's in the dataset are 4,000 and the total number of yes in the dataset are 2,000. So basically having the whole dataset equal to in the ratio of almost around 70-30. Now we can use sklearn's shuffle method in order to shuffle the records and then use it as the X feature. Of course, because we are using all the columns and we'll be removing the subscribed column from them. using the encoded DF and convert them into dummy variables, as the object data types are should be converted into dummy variables before using on the model. And so we have created the X and the Y features and use and split the data set into 70-30 ratio. Use the logistic regression model on the splits that train X and Y train splits, fit the data, and save the predictions on the test set of X in the predictions of Y. Now we want to check whether how many predictions were accurate on the model and how many were falsely predicted as positive. So that's why we'll be creating this confusion matrix. You can check the code over here. And out of, so the model is able to predict 141 actual subscription, and out of 434 were falsely predicted by the model. When we use the classification report on the models, on the values of test Y and the prediction that was made, you can see that the recall value of Y equals to 1 is 0.25 only, and the F1 score is 0.35, which is very low. So now we'll be using the ROC AOC curve score for the model that we have made. So we use the logic model on the predicted probability of X and save it in the predicted probability DF. And when we print a few of the records, you can see it on the top right, the predicted probabilities for the uh, index and the values. So those values will be used in test result DF, and an additional column will be used with the name of CHD1. When we use the score of when we calculate the score of ROC AOC, we are getting this score of 0.7. So plotting the ROC curve, this is the code that is used in to plot the curve. We have used it before also. So when we plot the curve, you can see that this is how the curve looks like, and the AUC score, area under the curve score we get is a 0.70. So this is the bank's data set that we are using, and we are using to predict whether the customers will subscribe to the term deposit term plan after the call or not. So this is our Y variable. We get the info of it, and we have a lot of object data types, as well as the count of yes and no's are very different. So it was an imbalanced data set. Because it was an imbalanced data set, we used upsampling and created the X and Y features. We uh, created the dummy variables for X features and saved the results of Y features, created the model after splitting the data set, and draw the uh, and draw made a confusion matrix for the model that we have created, and these were the values that were created rightly by the model, and these were the values that were wrongly predicted. And the classification score also, the prediction for predicting y equals to 1 was low. We calculated the score of ROC and AUC by combining the values of probability of 0 and 1 and adding the values of the uh, results on test y, making the column of CHD1 and storing the values of predicted probability DF. When we calculate the score, we get the score of 0.69. And this was the code used for calculating the, plotting the ROC graph. And this is the graph. And the AOC score that we get is 0.69. It's not ROC, it's AOC. For now, we'll be moving further with K nearest neighbors. So K nearest neighbor is a non-parametric algorithm, which basically means that it doesn't make any assumptions on the data. It memorizes the data and classifies the new observation that is added into the training data, added based on the training data. It categorizes. So the K in the KNN, which stands for K nearest neighbors, K is the hyperparameter. And when we try to find the model's optimal values for the hyperparameter, we call it the process is called hyperparameter tuning. The parametric algorithms are the ones that we have already been using, like logistic regression, which makes strong assumptions about the data and having a specific probability distribution. So the intuition behind the K nearest neighbor, you can see that we are plotting some points, and the points are divided into category 1 and 2, and a new data point has been added. And if the new data point is plotted and some of the nearest data points are calculated based on the distance in the graph, and if the distance is closer to category, whichever category, that new data point is classified into that category. So because the distance is closer to category 2, the new data point added is categorized as category 2. So this is the whole the intuition behind the K nearest neighbor. So there are many types of distances that we can use in the K nearest neighbor approach, because we are calculating the distance between 2 points. The Euclidean distance being the most widely used metric, and you can see how in the graph below how the Euclidean distance is calculated. Apart from Euclidean distance, there are Canberra, Minkowski, Jaccard coefficient, and Goa's distance for calculating the metric of the distance. So as we are using the K nearest neighbor, we're using through sckit-learn, and the parameters it takes are nearest neighbors, the number of neighbors to use, and by default the value is 5. Then by default the metric distance used is Minkowski, and the weights where the default value is uniform, where all the points is each neighborhood are weighted equally as the distance, which weighs points by the inverse of their distance. So how we'll be using is we will be using the number of neighbors as 5, and we'll be using the metric as Minkowski. We'll be using default values for other parameters as well. So our KNN KNN model is built and used on the train split of x and y, and these are the values it gives us for the output. You can see the metric value as Minkowski and the number of neighbors as 5. Weight has the default value of uniform. When we plot the ROC AOC curve for the ROC curve for the this KNN model that we have trained, we are getting the AOC score of 0.84, which is a good improvement. And making the confusion matrix on the KNN model that we have got, it is able to predict 433 actual uh, true predictions out of 575 values. So you can see the recall and the F1 score of the model has also improved when we see the classification report. Now we have used a number of neighbors or a value equals to 5. Now we want to see whether and also see the using the matrix of how different combination works and which are the different combination out of which different combinations are giving us the best uh, parameters for a model with the highest accuracy. So we use grid search CV. We have used grid search CV in the past. First parameter it takes is the model that we have been using or the model we want to use, if generally speaking. Then the parameter grid, then scoring based on what score we want to compare measure, but basically we are comparing the model's accuracy, right? So the scoring is the accuracy measure here. So we'll be using the ROC AOC and the CV, basically the value of the K in the K-fold cross validation. So the values that we'll be using are a number of neighbors as in the range of 5 to 10, and the metric for the distance calculation of Canberra, Euclidean, and Minkowski. So we use the tune parameters in order to save those values, and then run it within the grid search CV, save those values in the CLF, fit the data in the model, and the best score we get is a 0.82 for the model that we have created. And the best parameters that we have used, like a number of neighbors and the metric distance, the best parameters for the model that we are getting is Canberra, and number of neighbors are 5. So if you see that if you want to see the mean and the standard deviation of the model, you can use clf.grid score grid underscore scores underscore, and it will give you the mean and standard deviation for the different combinations. Higher the standard deviation can mean that it's overfitting. So we used the KNN model, then use the accuracy for calculating the models, and the score we get is 0.81 AUC score. We made the confusion matrix. This was the confusion matrix, then use the classification report, and we are getting good scores on them. Then we used grid search, basically used k-fold cross validation in order to, sorry, the grid search, used grid search CV, and using the CV value as 10, and recognized which were the best scores. So the best score for the model that we have made using KNN was 0.82, and the best parameters that we got were metric equals to Canberra and the number of neighbors equals to 5. So this was it for the session. To summarize, we started with regularization in order to deal with overfitting. We used a ridge, lasso, and elastic net and went with a lasso regularization. Then we started our new concept for K nearest neighbor, which is a non-parametric algorithm. We for we used ROC AOC score in order to see the KNN's accuracy. And for finding the optimal values in the KNN, we used a grid search CV, for which we got Canberra for the distance and number of neighbors as 5 for KNN. So this was it for this session 11.
Hey, thanks, Jamie. Excellent job. It was very interesting, and obviously lasso, L1, elastic, KNN, and optimization you took out. So what's the plan for the next session, session 12?
So next session will be a continuation of this KNN, but the model will be same. The different concepts will be used, like random for. We'll be introducing ensemble methods, and we'll be introducing the random forest in it.
Fantastic, fantastic. Excellent job, and keep doing, and we meet next again on Friday. And hopefully with that, the advanced machine learning part 2 will be completed, right?
Yes.
Thank you. Thank you very much, and I will end the session, and we can then on sec. So, stop the recording. Yeah.